Act 2. Okay, so we've had a bit of a look at macro scale weather phenomenon in terms of high and low pressure systems, fronts, cloud types, that kind of thing. The environment that we fly in is quite small scale, really, and there are some other kind of aspects that we should probably have a bit of a think about related to the small scale landscape features that we're interacting with that can affect our flying environment. So one of these is the sea breeze effect and the sea breeze front. So we end up with a situation in the summer where insolation warms the land quite quickly, but the sea doesn't warm up quite so fast, basically because water has a very high specific heat capacity. You have to put a lot of energy in it to cause it to increase in temperature a lot. So that basically means the land gets warmer quickly than the sea does, which means that the air above the land heats more quickly than the air above the sea. So you end up with a warmer, lower pressure area here. And when you have lower pressure at the surface, that tends to encourage air in from the surrounding areas and the lower pressure, less dense air to rise. And this effect basically develops in the summer at the coasts. We start off with a small scale circulation basically at the actual coastline, and then the circulation gets larger and larger as the day goes on, and the part of the circulation where basically the air is pushing along the surface from the sea and then over the land basically is called the sea breeze. There's a returning sea breeze that occurs above it, basically, the return part of the circulation. And where the air from the sea, which is quite a significantly different sort of air mass, it's moist and cold, it can have poor visibility, where that is basically pushing in and is basically moving the land air out of the way, you end up with a sea breeze front. A sea breeze front basically is at the point where this sea air is basically coming in inland, and it moves inland as the sea breeze develops throughout the day, basically. So let's just go back to that again. There's some characteristics of a sea breeze front that are quite obvious. You tend to end up with sea breeze front cloud development. You end up with something called which looks like a convection cloud. You end up with a stepped cloud level, basically. So it's on the land air side. You have a higher cloud base, and then you tend to have curtain cloud basically at the frontal point, which is basically tendrils of cloud coming down, and then a lower cloud base in the sea air area, and then the cloud dissipates quite quickly within the sea air. And the land air basically has strong convection in it. The sea air has a very small area of convection basically on the border, and then once you get significantly beyond that border area, there's very little convection available. So usually sea breeze front flights they're terminated quite quickly if somebody strays into the sea air part of the system, kind of thing, because the convection dies off. The other thing that's very much worth noticing is that as the sea breeze comes in and the front moves through past your observer's position, then normally you'll have a total reversal of the wind direction or a significant swing in the wind direction. Your classic place to experience that is somewhere like Devil's Dyke, where in the morning you'd have a light northerly wind and they'd all be soaring around on the hill, and then basically as the sea breeze arrives, the convection gets strong, and then the wind actually reverses and starts blowing over the back, kind of thing. And the smart people have managed to climb up to cloud base basically in the convergence zone, But anyone who hasn't climbed up to cloud base will then have to land, basically, because they're suddenly flying on the lee side of a hill, kind of thing. So that's a broad pattern of sea breezes. It's quite important to understand them because there are some safety considerations in terms of flying with them. The important thing in terms of the pilot exam is to remember how they form, which is the fact that you end up with a low pressure because of warming here and a high pressure because of, relatively speaking, colder air here. And the air basically blows from, at the surface, it blows from the high pressure offshore to the low pressure on the land, and then basically the pattern is reversed at altitude. So actually at altitude there's a high pressure here and a low pressure here, and that results in this very large scale circulation. Somewhere like the Maritime Alps, you end up with the situation that what's known as the returning sea breeze at altitude is very, very strong. So you can actually find in certain conditions in the Maritime Alps it's quite dangerous to fly in the middle of the day. There are certain places you shouldn't go, because if you get above a certain level you get into the returning sea breeze, which is a very strong wind blowing in the opposite direction, kind of thing. So sea breeze at surface level is blowing from the sea to the land, from high pressure to low pressure. And then in the low pressure area you've got this rising, here you've got descending, and then there's basically a reversal of the pressure at the top, so it's high pressure here and low pressure over there. Definitely worth knowing that for the pilot exam, or it certainly was a couple of years ago. So that's sea breeze development and the sea breeze front. Now, mountainous regions where you have mountains and valleys, large-scale relief. We're going to talk about two kinds of flow, basically. Anabatic flow, which is convective flow upslope, where the wind basically blows up the slope of any large-scale relief. It tends to develop during the day in hilly or mountainous areas. Particularly where there's not strong wind and there's sunshine. You end up with high pressure. Again, high pressure in the area where the wind is blowing from, blowing into a low pressure area where the rising is, and a convection cell basically is formed. You get cumulus clouds. And one of the reasons why this tends to happen is basically because if you have flat ground, as soon as the air moves away from contact with the ground, as soon as it is lifted, then it can't be heated any longer. Whereas if you have mountainous terrain, it's possible for the air to be lifted up the slope and still remain in contact with the ground. So this basically encourages greater heating, because the air is able to move up the mountain but still carry on being heated, whereas in the flatlands, as soon as the air moves away from the surface, it can't be heated any longer. So that's why you get upslope wind development. That's why you get this anabatic flow that develops in the mountains. And this results in, as well as up the mountain sides, you end up with this anabatic flow. You also end up with, in the valleys surrounding the mountains, you end up with a valley flow, basically, which is air that is pushing in to replace the air that's being drawn, or that's rising up the slopes, basically. So valley flow basically occurs during the day, and it occurs when anabatic flow has started, when convection is occurring on the mountain sides. Valley flow basically is pushing from the valley, from the plains, in through the valleys, basically up into the higher mountains, where all the convection is occurring. And there's a trick for knowing which way the valley flow is likely to be, which is that if you're flying in an alpine area and you come into a new valley area, more often than not, the valley flow is in the opposite direction to the river that is flowing in the bottom of the valley. So rivers flow away from the mountains, but the valley flow basically flows in the opposite direction. That's not always the case, but more often than not it is the general rule. So you have valley flow, you have anabatic flow basically that's flowing up the mountainsides, and that's how you get convection during the day in areas of significant relief. So we can see a little bit of a picture of a launch area here. It's probably some kind of British competition from many years ago by the look of it. It might even be Meyerhofen perhaps in the Austrian Alps. And you can see here that there's kind of like stratus, there's like some layer cloud knocking around. There's little bits of something going on here. That little telltale doesn't look terribly encouraging at the moment. Nobody's making great moves to launch by the look of it. This is probably quite early in the day before the anabatic flow is set up properly, kind of thing. There is an opposite kind of airflow that occurs at night, which is called katabatic flow. And basically what happens is you end up with the situation that air in contact with the ground is being chilled by a process of what's known as radiation, cooling. And this is basically that the ground emits long wave radiation and cools down. And the air that's in contact with it is then also cooled by conduction. And in exactly the reverse way to what was happening during the day, where you had a warm mountainside, when you have a cold mountainside, it's possible for the air to move down the mountainside and remain in contact with the ground while it's doing so. So it's able to basically move down the mountain and get colder and colder as it goes. So this basically then sets up a downslope wind and a convection cell in exactly the opposite way to the anabatic flow that we had during the day. And this is called katabatic flow. You have high pressure basically above the mountain peak and low pressure in the valleys basically. And this radiation cooling, which is basically driving the downslope flow basically, because the air is cooled by contact with the mountainside. As it's cooled, it gets denser, so it falls down the mountain. The wind flow is downslope. It develops once the ground heating is finished for the day, so that can be basically once one side of the mountain is in shade or once the sun has gone entirely. And the valley flow that's occurring at the bottom is now in the other direction. It's going in the same direction as the river more often than not. You can also end up with a situation where perhaps at the end of the day, if the sun's over here and say there's another mountainside on this over here, you can end up with this situation where this area is in shade and the mountainside over here is still in the sun. And in that situation, you end up with a hybrid. You end up with katabatic flow down the shaded mountainside into the bottom of the valley, and potentially still anabatic flow on this side, kind of thing. And that can result in basically huge, widespread areas of very smooth lift, magic lift, occurring in the evenings, kind of thing. So that's a consequence of katabatic flow, basically moving large areas of warm air upwards as the katabatic flow develops. A good place to experience that kind of thing is Saint-André in the evening, where you get very, very large areas of smooth light lift, or Piedrahita, where there's restitution at the end of the day, kind of thing. So, air masses. One of the things that you need to know in terms of predicting what the weather is going to be like and how the air is going to behave on a particular day is about basically air masses. It's about where the air has come from and what sort of characteristics it has. There are 6 main air mass types that influence the UK's weather, and they're all pretty much marked on this lovely diagram here. So if we sort of like start in the bottom right hand corner, we've got tropical continental air, which is basically coming from further south on the continent, coming round in a clockwise direction. We then have tropical maritime air, which is coming from significantly south of the UK, but from the Atlantic direction kind of thing, so it spent most of its time over water in a maritime environment. We then have an oddball called returning polar maritime air, which we'll come into in a little bit more detail shortly, but that's basically, it is essentially maritime air. We'll touch on why it's different from the other cases in a minute. Polar maritime air basically is very, very northerly. It's cold air, but it's primarily been coming from over the sea. Arctic air basically is coming directly down from the poles. It's very, very cold, very, very dry. It often arrives in a very, very vigorous kind of like jet fashion. And then polar continental air is similar to Arctic air, but it's probably had a longer journey over basically cold continental land rather than necessarily coming quickly down from the poles kind of thing. So those are the 6 different air masses that we tend to talk about when we're characterising the weather and the air that we're in the UK at different times. Looking at them in a little bit more detail, so tropical continental, it's warm air. It tends to be dry because it's been over land rather than over the sea. It comes primarily from North Africa. The air mass rarely reaches directly to the UK. You need a large area of southerly or southeasterly winds basically set up, coming all the way from North Africa, kind of like across Spain, up through France. Normally, when we experience tropical continental, we have light southerly winds. It's warm, dry air. The visibility is not very good. For flying, it's not terribly brilliant. It's quite stable. It doesn't tend to result in good cross-country conditions. So that's tropical continental. Tropical maritime is similar, except it's wet because it's been over the Atlantic Ocean. So this has come basically a long way over a relatively warm Atlantic area. It comes from near the Azores and the West Indies. As the air mass comes northeast, it becomes cooler and a little bit more stable. It tends to, we'll see it when we have southwesterly winds. Normally there are layered clouds. There's warm, humid air. There's often some precipitation, and particularly in the colder parts of the year, autumn, winter and spring, you'll often have sea fog associated with this particular kind of air mass. Polar continental. So this is cold air from northeastern Europe, and it's basically travelling west and south, and it tends to bring cold winds. It is being warmed from underneath as it comes over the North Sea, and so it's generally unstable because of this warming effect. Normally you have easterly or northeasterly winds, large amounts of cloud, very cold air, unstable showers, that sort of thing associated with polar continental. Polar maritime, this comes from the Arctic, Greenland and North Atlantic areas. It's travelling in a southeasterly direction. Yeah, I think that's wrong. That should probably say east. Southeasterly direction over the Atlantic. As the air mass is moving to warmer latitudes, the lower levels are warmed up again because the underlying sea and land that it's coming into contact with are warmer than where it's been previously. So it tends to be unstable. And typically you've got southwesterly to northerly winds. You have cumulus, clouds, good visibility, cold air. It's often quite good cross-country flying conditions when you have polar maritime air mass. And Arctic maritime is very similar to polar maritime, except that it's come, instead of from a kind of like northwesterly direction, it's come almost directly down from the north quite often, from the source region. These days it's often referred to in the press as a weather bomb. You'll end up with, very strong northerly winds and then it's going to snow or that sort of thing. Or a meteorologist might describe it as a polar jet, basically coming in and bringing in very cold polar air into the UK. Generally, you've got northerly winds, cumuliform clouds, heaped clouds, very, very good visibility. On a good day, you'd be able to stand on a hillside or fly and see, potentially 50, 60, 70 miles without any difficulty in that sort of air mass. It's very cold air. It will often have heavy and frequent precipitation, in the winter generally as snow kind of thing, that is associated with the instability and the very, very cold air. And then the oddball case that I didn't describe when I was looking at the diagram in full detail is returning polar maritime. And this is basically similar to the polar maritime case, except for the fact that the air's been on a bit of a detour first of all. The air basically has come. It's come south. It's come south in the Atlantic area, and then a depression which is kind of like in the vicinity of kind of like Ireland or west of Ireland has basically caused the air mass to swing around and then come back up to the UK or back across to the UK from a more southerly direction than it would have otherwise. So that's why it's called returning polar maritime. Generally, you're talking about it when it's polar air that's been forced south of 50 degrees north latitude by a depression, and then it swings northeasterly and comes from a sort of like southwest direction up the country. It tends to mean that you've got very cold air, but the lower levels have been warmed up quite a lot by the fact that that the whole thing has taken this southerly detour, and as a consequence of that, you've got the southwesterly winds that we already described. There's kind of like layered medium level clouds more often than not. You have good visibility because the air above the surface is quite cold, and it's generally unstable with showers. It can often be very good for cross-country conditions. Some of the best flights in the UK have been done in returning polar maritime air masses. Certainly the first flight I did of anything more than a few kilometres was in those kind of conditions. But because the instability is quite significant, then often you'll have showers, and it can be a relatively short-lived flight under certain circumstances. So that's air masses. The next thing really that we need to do is look in a bit more detail at convection, and how convection relates in detail to clouds and thermal development. So to start off with, let's have a look at a few kind of a bit of terminology definition and some kind of like useful formula kind of thing. So the first one is, this is actually a pretty standard formula that you can use to work out at what height cloud base is likely to be on a particular day. So if you're at the surface and you know that the air temperature is going to be 26 degrees or something like that, and you know that the dew point is another value, say it's 10 or whatever, then if you subtract the dew point from the air temperature and you multiply by 400, then that will approximately give you the altitude of cloud base in feet. And Wendy Windblows uses this kind of formula to try and work out what it thinks the cloud base is. Now, Wendy doesn't have a temperature and humidity sensor, so it can't tell you what the dew point is exactly, but there's a clever trick, which is that overnight the dew point, the temperature at which moisture starts to condense out of the air, is normally the lowest overnight ground level temperature. So at night, temperature tends to fall to the dew point, and then it more or less stops because the remaining temperature change is kind of soaked up by the condensation that forms. So if the dew point is the lowest overnight temperature, then your cloud-based calculation, you've got a simple way to work it out. You go on the weather forecast for the day and you look at the previous night's lowest temperature, you look at the highest forecast temperature for the day. If there's a big split between those two, then you know it's going to be a high cloud base. If it's a small split, it's going to be a low cloud base, not very good. So subtract one from the other, multiply by 400, and that will give you a bit of an indicator of whether you can expect to be flying around at 5,500 feet or stuck with your head in the clouds on the hill kind of thing. So that's a useful thing to understand, and we'll have a look a bit more about predicting cloud base shortly. So as I said, the dew point is the temperature at which moisture starts to condense out of the air when you're raising or lowering the temperature of a parcel of air, and it's dependent obviously upon the pressure and also upon the relative humidity, the amount of water vapour that's actually in the air. Then we've got some other terminology associated with thermal growth, development, activity, etc. Lapse rates. So a lapse rate basically is a change in temperature with height. I mean, everybody knows that as you climb up a mountain it gets colder, or you fly higher it gets colder, etc. There are a number of different types of lapse rates that you need to understand. We'll look at those shortly, but a lapse rate in general is a change in temperature with height. There's another term which is used in association with lapse rates, which is this physics term adiabatic, and that basically means that no heat energy has been added or removed by a particular parcel from a particular parcel of air. So it basically is saying it's kind of like if everything else remains equal. If you take a parcel of air and you do something to it, but what you're not doing to it is adding or removing heat energy from it. So that's adiabatic. And if you want to know a little bit about the dew point in relation to ground level, if you have a certain dew point at ground level, there you can basically say that there's a dew point lapse rate, which is the way that dew point changes as you move up in altitude. And basically the dew point falls by 0.5 degrees centigrade per 1,000 feet up to the point you get to cloud base. Once you get to cloud base, there is no dew point lapse rate any longer. You've reached the dew point. It carries on with the saturated adiabatic lapse rate, which we'll talk about in a moment. So that's a specific kind of lapse rate that tells you basically how the dew point changes with altitude. Okay, so some more lapse rates. Now this is all getting fun. The environmental lapse rate. On a particular day, if you sent up a radio sonde underneath one of those little weather balloons that everyone likes to use to send GoPros into orbit these days, if you send up a radio sonde, you actually get a plot of the temperature as the balloon goes up. And that plot of the temperature shows the environmental lapse rate. It shows you what the temperature profile of the environment is on that actual day in your particular piece of air. Now that varies from air mass to air mass and from place to place on the surface of the Earth and from week to week, etc. But it averages 2 degrees centigrade per 1,000 feet. That's a rough average value. Now, if you take a parcel of air at ground level and you move it up, then that parcel of air, as long as cloud base is still above your head as you're moving that parcel of air up, that parcel of air cools at what is known as the dry adiabatic lapse rate. And that rate is 3 degrees centigrade per 1,000 feet. So that's basically, you take a balloon, for example, full of air, and you move it from the valley to the top of the mountain. You can predict that as long as it hasn't started to condense inside that balloon, you can predict the temperature of the air inside that balloon basically by applying that 3 degrees per 1,000 feet formula. So it cools at 3 degrees per 1,000 feet up to reaching the dew point, up to cloud base. Once you get to cloud base, once the air inside your little balloon has basically reached 100% saturation, 100% relative humidity, then as you cool it further by lifting it, there's a new process going on, which is condensation, which actually alters the balance of the lapse rate, basically. And this is called the saturated adiabatic lapse rate. Indicates the rate at which air cools above cloud base, above the dew point, and it's lower. It's 1.5 degrees centigrade per 1,000 feet rather than 3 degrees centigrade per 1,000 feet, and that's basically because some energy is recovered, is put back into the air by the condensation that's occurring. It's called the latent heat of condensation, I think, from my memory. So you have these two, if you take a parcel of air, you have these two lapse rates that apply as you move it up and down in the environment. You have these two lapse rates that apply. Before you get condensation occurring, it's the dry adiabatic lapse rate, 3 degrees centigrade per 1,000 feet. And after condensation starts occurring, after you've reached the dew point or cloud base, then you have the saturated adiabatic lapse rate is the rate of change of temperature, 1.5 degrees per 1,000 feet. Other terminology associated with lapse rates, rates of cooling in the atmosphere. An inversion is actually an area of the atmosphere where the temperature rises with height. So, as we said, the environmental lapse rate is normally about 2 degrees per 1,000 feet. That's the way the profile is on average over the whole surface of the Earth. But you get some areas on the surface of the Earth where at certain heights you can actually have the air warming as you get higher rather than cooling, and that's known as an inversion. In flying, there's a frequent misuse of this term, in that people get to what they call a stable layer and they can't climb above it, and they say, oh, I got to the inversion. Well, it wasn't necessarily an inversion, it was just a bit more stable than the bit that you were in before. In fact, more often than not, it probably wasn't an inversion necessarily. When someone says, oh, I got to the inversion, you say, no, you got to the stable layer. Are you sure the air was getting warmer above you, or was it just not getting cold quickly enough? So less of an inversion than an inversion is an isothermal layer, and that's basically where the air isn't getting colder, it's remaining at the same temperature as you move up through it. And then we have these two terms, stable and unstable. And this is always where the fun starts, trying to work out how to explain these bits. So when the environmental lapse rate is lower than the dry adiabatic lapse rate, that basically means the environmental lapse rate is low, so the rate at which the environment decreases in temperature as you move upwards is low, so that means warm air aloft. So if you have warmer air aloft, because the ELR is relatively small in comparison to the dry adiabatic lapse rate, then you have stable conditions. So a parcel of air basically will soon find that it wants to return to its previous level. And that's basically because of the gas laws. The pressure and temperature change basically mean that as you raise a parcel of air up, in comparison to the environment, it becomes heavier than the air around it is. So in those conditions, the parcel of air that you move adiabatically becomes heavier than the surrounding air, so it wants to return to the height that you started it off from. In unstable conditions, the environmental lapse rate is high. It's larger than the dry adiabatic lapse rate. So that will basically mean that as you move a parcel of air up, the air around it is colder than it is. You have cold air aloft, relatively speaking, So that means that the air surrounding the parcel that you're moving is heavier. So as you move the parcel up, the air around it is heavier, and therefore the parcel of air that you've moved then goes, okay, I want to carry on moving, I want to keep moving. I don't want to go back to where I came from. Somebody's disturbed me and I now want to keep moving in that direction, kind of thing. So that's the difference between stable and unstable conditions. It's to do with the environmental lapse rate on the day. When the environmental lapse rate is small, a parcel of air that's disturbed, we'll find that the air around it is trying to force it back down to the level that it was at before. On an unstable day, the opposite occurs. When you move a parcel of air up, then the surrounding air basically will then be progressively heavier and heavier than it, and so the air will want to carry on accelerating up. So on a stable day, you don't get good thermal development because the lapse rate is trying to discourage, the environmental lapse rate is trying to discourage thermal development. It's trying to force the air back to where it was. You have to put a lot of heat in before you end up with convection occurring, and the convection gradually gets whittled away by mixing around it. So you end up with little tendril thermals that are reaching up through the atmosphere and gradually petering out. And on an unstable day, in an unstable environment, a very small parcel of air that's moved a little tiny way gradually starts to move more and more, and it gathers more air around it. You end up with basically very large thermals that are very well organised and are very easy to fly in, basically. So that's the difference between stable and unstable, and it's all to do with the size of the environmental lapse rate. When the environmental lapse rate is low, stability. When the environmental lapse rate is high, instability. And to think about it in terms of air mass, low environmental lapse rate means the air is relatively speaking warm at altitude, unusually warm, and high environmental lapse rate means that the air mass is relatively speaking cold at altitude. So, having got through that without confusing myself too much, and hopefully not you will be able to read it again. This is probably the worst slide, actually, until we look at these ones. So here's a very simple diagram showing, a simplified environmental lapse rate on a day. You can see that the temperature at ground level is 20 degrees, and then there's a nice looks pretty much like 2 degrees per, it's almost like it's in a textbook rather than a real atmospheric case. 2 degrees per 1,000 feet kind of thing. The air is cooling at this kind of like fictional standard environmental lapse rate. So at 5,000 feet it's cooled by 10 degrees, 2 degrees per 1,000 feet. Yes, that's, if only it was all that simple. Now this is a bit more like a real scenario. The first thing to do is to have the thick line here is, again, it's an environmental lapse rate. But you can see that the environmental lapse rate has like a toe on it. So you've got this kind of like standard, that's probably pretty close to 2 degrees again. But then down here there's this little toe at the bottom. And that is a pattern that you would often see if you looked at a tephigram or a temperature plot. You'll often see that there's a little toe in the environmental lapse rate at the bottom, and that is because the air close to the ground is being warmed up by insulation and by convection. So the lapse rate comes down, and then it's like, and now we're into the bubble of warm air close to the ground. So you have this bubble of warm air near to the ground. Let's say it's 25 degrees centigrade, and a thermal breaks away, basically. So the ground heating of the surface air, 25 degrees, a thermal breaks away, and it cools as it rises, not at the environmental lapse rate, but at the dry adiabatic lapse rate, which is 3 degrees centigrade per 1,000 feet. So that's a shallower line kind of thing. It's moving up, and as it moves up, it's getting closer and closer to the environmental line. And when it suddenly finds itself that it's met the environmental line, it's no longer warmer than the surrounding air. When it's no longer warmer than the surrounding air, it doesn't have any buoyancy any longer. When it's warmer than the surrounding air, it has buoyancy. As the dry adiabatic lapse rate brings its temperature closer and closer to the environmental temperature at that height, the buoyancy gradually decreases until it gets to this point at which it has no buoyancy. Now, it might overshoot a little bit, but basically, it's going to get here, and more or less, convection is going to stop around about there.
Does that mean that then thermal strength is the bigger the difference between those two lines, the faster it wants to go up?
Generally, yes. The amount of energy that's available for thermal development, for convection development, is related to the distance between the dry adiabat, or between the environmental adiabat and the dry adiabat, basically below cloud base. So you might have this is like relatively speaking quite a stable day, in that close to the ground there's some heating going on, which is enough to basically cause thermal development, but then as the thermal gets higher, it kind of like peters out a bit and then it stops, kind of thing. So it's probably the thermals will be gradually being whittled away, and they'll get squirrely, and as you get to 5,000 feet, it will start to get very difficult to climb. So that's quite straightforward. What we haven't brought into this yet is the idea of the dew point and clouds, and the transition between the dry adiabatic lapse rate and the saturated adiabatic lapse rate. So in this particular case, we're showing a diagram that it just climbs all the way at the dry adiabatic lapse rate until it reaches the environmental line. The environmental line, at that point, it stops. So that kind of means that there is not likely to be here any cloud development due to the thermal convection. If we go and have a look at a more complicated example, here we've actually got thermal growth in the situation where the dew point is met before the thermal stops. So on this day, clouds have formed with the cloud base at the dew point, and the cloud tops are limited basically by an inversion here. So there won't be any thermic development. The thermals will peter out at this point. Convection stops at this level. So you have, again, the same toe at the bottom of the environmental line, which indicates ground heating. And you have a thermal breaking away and rising at the dry adiabatic lapse rate. But we also know that today the dew point at ground level is, say, 17 degrees or something like that, 15, 16 degrees. And if you plot that dew point upwards at the dew point lapse rate that we talked about earlier, then eventually that dew point lapse rate will meet the dry adiabat line that your thermal is travelling up on. And where those two meet is where you start to get condensation, where you've reached the dew point, you've reached 100% relative humidity, you start to get condensation coming out of the water vapour in the air. At that point, the rate of cooling of your parcel of air changes from cooling at the dry adiabatic lapse rate to at the saturated adiabatic lapse rate, which is 1.5 degrees per 1,000 feet. So it's a much steeper line kind of thing, basically, in terms of it goes up with much less loss of temperature. So you can see here that initially we're moving closer and closer to the environmental line, kind of thing, and then here we're now moving maybe away from it a little bit, kind of thing. So there's more energy becoming available here. Here the amount of energy is kind of like decreasing as you get close to cloud base, and then there's a bit more becoming available here. And then thankfully we've got an inversion, and basically the saturated adiabatic lapse rate meets the environmental line here, and that basically means that you can predict that the clouds are only going to go up to that point, kind of thing. So if we look at how we could rearrange the diagram a little bit, if the thermal broke away at a lower temperature, here for example, and followed the dry adiabatic line up, then it would have met the environmental line here, and we would have had a much lower top of convection, but we would have also had a blue day kind of thing. If there was less surface heating, so the temperature didn't get quite as high, we would find that the thermal stopped below the dew point level being reached. The other possibility is that if you move the dew point, if you basically moved the dew point kind of over here and plotted it up, then again the dry adiabat would potentially meet the environmental line before it met the dew point line, and you wouldn't have cloud development. So yeah, as I said, the energy available to develop convection is kind of increasing here, then it's gradually decreasing, and then it's increasing a little bit again here before it shuts off. So this kind of like steeper gradient here encourages lifting above cloud base, whereas this shallower gradient here basically is causing the thermal to slacken off before it gets to cloud base. Does that all make sense?
Question. Magically, we've got the inversion of the cloud tops. Where does that come from in your example? Is that typical, or just you chose to show?
That's purely here to make this example illustrate the three kind of like key points. The low-level situation where you've got heating and the breakaway of the thermal, the mid-level situation where you've got dew point being reached, and then the situation at the top of convection where basically convection is limited by an inversion. Now you could actually have the situation where, you know, instead of it being an inversion, you could just have the situation that this environmental lapse rate, it wasn't actually an inversion, it was just a lower environmental lapse rate rather than a hard inversion. This is normal, sort of like inversions, or kind of the situation where the environmental lapse rate curves back in that direction. At altitude, that normally tends to occur on the edge of high pressure systems. And this sort of pattern, though not necessarily with a very hard inversion like this sort of pattern where you have limited cloud tops, so maybe a 2, 3, 4,000 feet of cloud development or whatever, that's classic good cross-country flying weather kind of thing. If you don't have a pattern of the environmental lapse rate above the dew point level, above cloud base, that causes a limit to convection development, then the cloud will basically get very tall, you'll get ice crystal formation, and before you know it, it will be raining. So the reason that that's there is it illustrates the classic example that is good, and you want to be able to observe, you ideally want to be able to look at a plot and say, okay, today there is no lid on the conditions, nothing is stopping it from, there's no limit, it's deep convection. So therefore I need to watch out, it could potentially storm or is likely to storm. Whereas on another day you might say, well, there's a good region of convection below this height, and then you've got a reasonable depth of kind of like cloud development, and then there's a significant lid on the whole shebang, the whole set of affairs, that basically means that you won't get overdevelopment, you won't get storm formation, that sort of thing. So why the inversion is there is to illustrate the best conditions, and also to illustrate how you forecast whether there's a lid or not and how high the lid is, kind of thing.
Can I ask another question?
Yes?
If that's a real situation on a real day, then the fact that you're using the saturated air lapse rate, if I understand it right, means that that's what's happening inside the cloud.
Yes.
What's happening at that level, quarter of a mile from the cloud?
Outside the cloud.
Because that's what you want to do, isn't it?
Well, that's debatable. Depends if you like flying in clouds or not.
Why did you look at me then?
I wasn't. I was just looking. We all like flying in clouds, don't we? Really, a little bit. It's just round here there might be gliders in them, so it's not a very good idea. So
we're flying in clouds, basically.
no. Let's this dew point down here, yeah. On a real tephogram plot rather than an idealised one like this, there is actually a dew point line which goes up, which basically shows the moisture level and the dew point, the environmental dew point at all different levels in the atmosphere. Now, if the environmental line is kind of like over here in terms of temperature, and you're flying in a bit of air that's not cloud, then you're obviously in a bit of air where you're not at the dew point. And that is basically because air that's close to the ground is normally receiving moisture from the ground. What's the term? Is it evapotranspiration, where like plants and that sort of thing and everything, they're basically putting moisture into the air. Similarly, you've got evaporation because the sun is heating the ground, which may have been made wet overnight by the formation of the dew, etc. So normally, you would actually find that there's more moisture in the air at ground level than there is at altitude. Yeah, which means that when a thermal parcel rises up, it meets its dew point before the dew point of the air it's moving through. The air it's moving through is less humid. So if you fly away from the cloud, you're flying clear air because it's less humid than the moist air that's been lifted from the surface by the thermal convection. Does that make sense? Maybe. You'll be able to watch it again and see whether it makes sense later.
There's a difference between believing it and understanding it.
Yeah. I mean, generally, yeah, you can. There's a very if you're flying at cloud base and you fly into a blue area, you'll normally find that once you've flown more than 50, 100 meters into a blue area, there's no lift any longer, and that's because you're not in the convective parcel any longer. If you remain in the convective parcel, you remain in the more moist air. And you will basically then fly into the base of the cloud, potentially, and go up in the cloud. And you're in the more moist parcel of air there. If you fly away from the cloud, you fly out of that convective parcel. And even if you were able to climb up outside the cloud, you're actually in a bit of air mass that's less moist. So that's why it's blue, rather than fluffy and white and wet kind of thing. So that shows a kind of like, an overall pattern of thermal development and how the dew point and the dry adiabatic lapse rate, the dew point lapse rate and the dry adiabat, they meet. At that point you get cloud base, then you move to the saturated adiabatic lapse rate, and where your parcel of thermal air, where those two lapse rates or whichever one you're following meets the environment line, then convection stops. You will need for the exam to be able to give you a simple example of something like this with an environment line drawn on kind of thing, and then you'll be able to, they'll tell you, okay, given that this is one lapse rate and this is the other lapse rate, please do a plot and tell us what height you think cloud base is going to be at, and do you think it's going to be limited and stuff like that. So understanding how to basically plot these lines and see where they stop or where they change from one rate to another is quite important. So that's most of the things that I think you really need to know in terms of theory for examinations and that sort of thing. It's worthwhile having a bit of a look at where you can get information to help you with your flying on a day-to-day basis kind of thing. back in the day, people used to get weather information from all sorts of places. And in fact, I edited some things out of this presentation earlier, which I don't think anyone's probably used in 10 years. Volmet? No, yeah, exactly. Who would go to the hill and take an airband radio and then tune into somebody from the far end of the country telling some aeroplanes what the weather's like? No, you wouldn't do that nowadays. Online is obviously where we can get most of our weather information. It used to be that there's good BBC forecasts on the TV, but they've been dumbed down sufficiently that you rarely see a synoptic chart nowadays, only if they're trying to point out some silly weather feature that they think has merit. So if you want to see synoptics, you really need to go onto the Met Office. Well, it's not actually on the Met Office website. It's actually the best place to get the synoptics from is weathercharts.org, who have a special page that shows all of the synoptics for the next 5 days or whatever. Synoptics for me are always the first place to go and look for weather information, because they, once you can read them, they give you a huge amount of information. The closeness of the isobars tells you whether it's going to be too windy or not. Frontal information and the high and low pressures tell you whether it's going to be raining or what the what the cloud development is going to be like. The direction of the isobars gives you a broad indication of the air mass, i.e. what air characteristics are coming in, etc., etc. And very soon, if you study synoptics on a regular basis, if you look at them, you'll soon start to say, oh yeah, I see that pattern later in the week. That's going to mean a good cross-country day, or that's going to mean a good flying day. So I would always say that synoptics are the first thing to look at. If you can stomach looking at synoptics, do so. The BBC weather site has got a lot of kind of like very simple pictogram, kind of like, oh, in Sheffield it's going to be 5 miles an hour, it's going to be northeasterly, it's going to be 27 degrees, that kind of thing. That's useful, but it's quite difficult to relate to the weather at the top of the hill, and it's quite difficult to relate to whether it's going to be a good XC day or not. So I don't tend to use that sort of thing very much. The other end of the scale is RASP, which is Regional Atmospheric Soaring Forecast Platform or something like that. This basically is a very small scale weather model of the UK that is optimized to twice a day produce extremely detailed plots of soaring weather information. So how strong the thermal strength will be, how high the cloud base will be, what the cloud depth will be, what proportion of cloud there'll be, etc., etc. Whether there's wave development, all kinds of things like that. So RASP is very, very good. It's very, very detailed. On more than one occasion, on days where there's been no flying throughout most of the UK, RASP has enabled me to go somewhere and have a nice afternoon's flying, and almost everywhere else has been rubbish. The forecasts are often that good on RASP, kind of thing. They can pick out little areas where it will be flyable. But they also give you a very broad idea of the day, and they'll highlight, if you're a cross-country hound, they will highlight the areas of the country that are going to have the best conditions on a good cross-country day. So it might be that it's going to be cross-countryable everywhere, but in the southwest of England it's going to be particularly good. There'll be like a 6-hour period where there's very strong thermal development, high cloud base, good conditions for flying a long way kind of thing, whereas other parts of the country might not be so good. RASP is very good at showing that variation between different parts of the country once you learn to read it. To go along with RASP, satellite pictures are often quite a useful tool if you want to look at high cloud development and whether a particular area of the country is going to be shut down by cloud, or whether it's going to be clear kind of thing then, or how a front is progressing towards the country in comparison to the forecast. Then satellite pictures can help quite a lot with that. Falling out of use a little bit nowadays because RASP is a much easier tool to interpret. The next one though is really, really useful, and particularly for people who are chained to a desk during the week. you often want to know, is it going to be flyable next weekend? And the Met Office have an annoying kind of horizon, which is like 4.5 days. So that basically means when you look on Sunday, you can't see any further than kind of like Thursday, Friday kind of thing. You can't really get an idea about what the shape of the weather is going to be like next weekend. Well, there is a specific organisation, sorry Brexiters, the European Centre for Medium Range Weather Forecasting, so we won't be able to access that shortly. But anyway, they provide 10-day forecasts, and they provide a synoptic, and the synoptic shows it doesn't show frontal development, but it shows broadly the pressure patterns, and it also shows areas of high wind speeds. So you can basically see whether there's going to be high winds. You can look and have a good guess whether there's going to be frontal development in the area. And it's good enough to give you a bit of a clue about next weekend. So if you're planning on a Sunday or Monday or whatever to try and work out what to do next weekend, then ECMWF is a very useful tool. Live conditions. There's Wendy Windblows, if you want to subscribe to that, which is a network of weather stations on a lot of flying sites across the UK. It's very good for ringing up and getting a bit of an idea about what it's doing at a particular location. It can be accessed both online and via telephone. Useful tool, certainly I used to subscribe to that in my first 5 years of flying kind of thing to give me a bit of an idea. The other tool that's often very good for live conditions is XC Weather. Now, XC Weather basically takes airfield reports. So all of the airfields across the UK, on an hourly basis or half-hourly basis, they submit current Met conditions reports, and those current Met conditions reports are compiled automatically by XC Weather into a weather map that basically shows you the pressure, it shows you the wind strength at all of those locations. And certainly for here, there are some very useful rules of thumb that you can use basically to say, well, if XC Weather says this, then I think it's going to be flyable here, or I think it's going to be borderline kind of thing. Generally, if Manchester says 10 miles an hour or more, it's very borderline in the Peak District and you might not be able to fly. If Manchester says 5 to 7 or 5 to 8, then you've got a much better chance. So XC Weather is a very good tool. And then you've got some kind of sites that basically collect all sorts of resources for you to look at, because, well, if you don't like one forecast, it's always a good idea to have a look for another. Eventually you might find one you like. Weathercharts.org has a huge number of resources that you can click through into, showing various different things, not just the surface level pressure synoptic plots that I've indicated up there. And there's a site called Weatherjack, who's a guy who used to run a manual forecast a bit like RASP, but now he maintains a collection of weather links that shows pretty much everything that you could possibly want. So that's a reasonable selection of where it's good to get forecast information from online. Here's a satellite image. So this shows a bit of an example of the kind of thing that I said you might want to use satellite images for. If you were trying to work out whether it was going to be any good to fly cross country on this day in the peaks because of the incoming warm front here, probably, then you would probably say, based on this latest satellite picture, you'd probably say, no, I think it's had it. Because the high cloud is here already, and in another 2 or 3 hours the high cloud is going to be a lot quicker kind of thing, so a lot thicker. So that's the kind of way in which people use satellite images, but obviously they're not as, they require some effort to read, and they're not as definitive as something like RASP or one of the detailed forecast sites. This is a medium range forecast, so Sunday, yeah, exactly. Sunday 31st of January. So that's looking forward from a Sunday to a Wednesday kind of thing. You can see that we've got isobars, so we've got areas of high and low pressure marked, but you can see that the yellow and green areas, those actually mark wind strength at the surface. So if you have an area that is that doesn't have high wind markings, there's a chance. On this particular day, you would probably say that chance is slim because there's a high wind marking here in the North Sea, and the isobars are quite close together across the UK, kind of thing. But certainly it looks like if you were on the North Cornish coast, you might be able to do a bit of coastal soaring, or in Wales potentially. But that kind of, you can see the broad pattern. You can see, for example, that there's a northerly flow. You can see where the high pressures are, etc. You can see how close the isobars are together. So because it goes further out, it gives you a good chance to make a prediction about next week, rather than just falling off the end of the Met Office cycle and going, I don't know what it's going to be. I don't have a chart. The old stuff that you might need to know, old things about where you can get forecasts from. Well, Radio 4, the shipping forecast. Yes, if you really want to know, and you really don't have access to anything else, you can turn on the radio at nearly 1 o'clock in the morning. You get a delightful piece of music, and then they tell you where all the high pressures are, and the low pressures. They tell you what they're doing. They tell you what the observations are at lots and lots of different places. And if you were absolutely desperate, probably if you were on a small boat in the middle of the Atlantic or whatever, then you would plot those out and you would get an indication of what the weather chart looks like. These days, you're not going to do that, and you're not going to need to do that. So unless you like listening to Sailing By, which is a very nice piece of music, I wouldn't recommend that as a source of information. Similarly, Volmet. This is a voice service on VHF airband, and it's transmitted by 4 or 5 different frequency transmitters around the UK, and each Volmet station basically cycles through a list of kind of like current conditions reports and forecasts for a set of airfields, kind of thing. If you have an airband capable radio and you feel the need to listen to what a Volmet report sounds like, then you can go and Google the frequencies and you can listen to them, and you will find it absolutely thrilling. But I don't recommend it. You need to be really bored to use these old ways of doing it. This one is a bit of an interesting one. There may be something, I don't know why, there could well be something on the examination associated with this. There is an acronym which you might hear in relation to airfield weather reports called CAVOC. And it literally means ceiling and visibility OK. And the conditions that it describes are basically that the visibility is 10k or more, there is no cloud below 5,000 feet above the aerodrome elevation, and there are no cumulonimbus clouds at any level. There's no significant weather at or in the vicinity of the aerodrome. Why you might need to know that, I can't imagine, but you should know broadly what CAVOC means. As I've already described, there are Met reports from airfields which are available, and the general way that we access those nowadays is through XC Weather, because XC Weather goes and it compiles them all. If you've got an airband radio again, you can tune into the ATIS, Air Traffic Information Service reports from a particular airfield, and you can hear that they'll give out a METAR report on a regular basis, and it will describe how much cloud cover there is, what the temperature is, what the wind direction is, etc., at the airfield, what the general weather conditions are. As I've said, those all appear online somewhere, and XC Weather does a very nice job and downloads them at a regular basis and compiles them into lovely maps. So have a look at XC Weather and you'll appreciate the information that comes out of an airfield report, Met report. Windy wind blows again. There are other online weather stations that are about. Often it's difficult to know what location they're in though. For example, There's one in Buxton, which if you're trying to work out whether there's any wind in the peaks or not, you could have a look at that. But I don't know what house it's on. I don't know whether it's in the bottom of a dip or on the top of a bit of a hill. If it says one thing, I don't know whether the bloke's been outside batting the little anemometer cups round or whatever, or whether a sparrow's sitting on it or whatever. They are less reliable, generally speaking, than Wendy and the METAR reports on XC weather kind of thing. So unless you're flying somewhere where there isn't any other kind of like information, other weather stations are generally not used very much. More web forecast stuff, weathercharts.org, yeah, XC weather, I think we've talked about all this. RASP, yeah. RASP again, soaring plots for the UK. If you want to know more about RASP, Judith Mole's podcasts, basically there is a podcast that describes using RASP in detail, describes the kind of parameters you need to look at, how to use it, what they mean, that sort of thing. RASP is a whole evening's discussion in itself in terms of, because there's so much information there. There are probably 40 different atmospheric parameters that you can plot, that you can see plots of kind of thing, and probably only 8 or 9 of them are relevant. So yeah, if you want to find out more about RASP, go and have a look at it. Once you've played around with it a little bit, then maybe go and find Judith's site and see if you can find the RASP podcast, because that'll give you a bit more information. And finally, apart from the fact that we'll make the slides available online, so I'll post these will be posted on both the Facebook group and also in the website. We create a new thread in the forums. Pilot exam notes for meteorology, if you can find pilot exam notes elsewhere online, then those are probably good because the Met stuff doesn't change. For other parts of the pilot syllabus, particularly air law, be very careful about where you get other pilot notes from, because they may have been not updated to reflect latest developments in air law kind of thing. So for Met, if you can find pilot exam notes anywhere else, then feel free to use those, but we'll publish these. For the other ones, take more care. The notes here, which we'll publish online, and have a look at some of these if you want to develop your knowledge any further. Any questions? Do we want to look at anything again? No? Do you all want to run home in fear? Well, thank you very much. I hope it was reasonably useful. Okay, cheers.